Happy for this rejection.
Get started. How was everyone's homework? Good? Okay. So I think I hosted like 3 office hours last week, but I think the last one, the one before class, one person show up. So I guess I'm going to move my office hour maybe to Monday or Friday. That would be better. I guess the Wednesday office hour is already too late. But like I said, if you just ping me on Slack, we can meet anytime. So when we meet, I try to make it ad hoc office hour, so everyone else can also join. Good. So last class at the end, we talked about how to overflow the return address of the 32-bit and also 64-bit program, the stack. Then you can jump to the print flag function, right? So that's what we did last time. So right now, the only difference between the 32-bit version and the 64-bit version is the size of the return address, the size of all the different data structures and also integers. They're all different. Otherwise, so far, it's the same. Today, we're going to learn something. You can say the 32-bit and 64-bit are actually different in hacking. So first, we will learn how to return to a function with parameters. So previously, we returned to print flag function, and that function didn't take any parameter. You just override the return address. You didn't give it any parameter, right? So let's take a look at if we want to return to an arbitrary function, and that function may have different parameters, many more than one. So how do we do that? Okay, this sounds straightforward, but if you really dive into it, you see there are some tricky things. So we need to understand those. We need to understand them. Okay, so this is overflow return to. We're still looking at the 32-bit version, 64-bit actually the same. Let's see. The main function, we have argc and argv there. The main function first print out the address of a function called print secret. We use %p there to print out the address. Then main function calls val-foo. That's my hint. So it means that function has a vulnerability, val-foo. After that, it print out IPT-the-foo. So if you cannot exploit the vulnerability in val-foo, then the control flow will go to the last printf, IPT-the-foo. So you do not get a flag, right? So inside the val-foo, we have a local variable buff. It's 6 bytes. In the C code level, it's 6 bytes, but I told you many times, the compiler may reserve more space for that. Then it calls gets, which is a C library function. Gets will get input from the command line, from stdin, basically, standard input. So in this class, I'm using all kinds of functions here. We use the string copy, we use the fgets, we use gets. So fgets, I think fgets showed up in the homework. So fgets, it does have a parameter saying how many bytes you want to read, right? So it sounds a little bit more secure than other functions like gets or string copy, because those functions do not specify how many bytes you want to get. It will only end when it reaches 0 or end of line, whatever. But those fgets, those kind of functions, they are still dangerous. They may still override things because the number you specify there may still be bigger than the size of the buffer. Right? Yeah.
I think the homework was f-rates, if I'm not wrong.
F-rates?
Yeah.
Yes. I think the homework may be, F-rate, yeah. Then the function just return, okay? So very simple, only one line of code there, gets. Then there is another function in the address space called print secret. And this function takes one argument, I, and at the very beginning of the function, it compares whether i's value equals like 1, 2, 3, 4, 5, 6, 7, 8. If I is that value, it will call print flag. Otherwise, it print I pt the full. So, okay. So you can say in the address space, there are two functions we can utilize. One is print flag, because it is called here, so it is already in the address space. Then it's print secret. You actually already learned how can you directly return to print flag, but that's what we're not going to do here. Here we only want to return to print secret and at the beginning of here, because we want to learn how to set the parameter, the argument here. Okay, so this is what the stack looks like at the end of Overflow. Right? While we running the program, we're already at the end of Overflow. Overflow is going to return. So when Overflow is going to return, there is a return say. This is a say statement return. This statement eventually will be compiled into multiple instructions. And let's say this is what the stack looks like. At the beginning, here, first we have the return address. So where does this return address point to?
Printf IPT the main function.
Yes, somewhere there.
Yeah.
Yes. Then we have the saved EBP, and the register EBP points to the saved EBP. Then lower than that, in the address space, we have buffer. We don't really know the size right now. So let's say we have a buffer overflow here, because it's taking input from standard in. So we can overflow this. So we can overflow the whole thing, right? We can overflow the buffer. We can overflow the saved EBP. Let's say we just put A there, random garbage value A there. Then on top of that, we put the address of print secret there. Okay, so this is what we're going to do. Then we have the last three instructions in the Overflow function, which is the epilogue of Overflow. Those three instructions are move EBP to ESP, pop EBP, then return. Okay, let's say what do those three instructions do? First, move EBP to ESP, which means before that, the ESP is pointing to somewhere here. Now we are copying the value of EBP to ESP, so both of them right now point to this saved EBP, which we already overwrite. We have 4, so here I'm trying to say 4 letters of A's. Then we have pop EBP, which means whatever is in the saved EBP, because ESP points to that place, whatever ESP points to will be popped into the register EBP. So now the register EBP has the value AAAA. Then ESP, because there is a pop, it moves up 4 bytes. Now ESP points to the address of print secret, right? Then we have our return instruction. The return instruction will pop whatever ESP points to EIP. So the CPU will start executing from there, right? So after this, EIP will have the address of print secret. EBP has 4 A's. ESP moves up to point to here. We don't really know what is here, okay? So what is the next instruction to be executed at this moment?
Print secret?
Exactly. So we are going to execute the beginning of print secret. Yeah, go ahead.
These 3 instructions, they're similar to the leave instruction, right?
Exactly. Leave is those 2. It's equivalent.
It's not the 3? There's
Not the 3. After leave, you still need to do a return.
Okay.
So in the programs in this class, we do not say many enter and leave. So I'm not emphasizing that part, but they are equivalent to that. Okay, so the next instruction we're going to about to execute is the beginning of print secret. Yeah, anyone remember what is the beginning of a new function?
Lower ESP.
Even higher than.
EB.
So actually, at the beginning, you have push EBP, but you probably already see this multiple times. There is under BR something. Yeah, under BR32. That's a security feature. That is a control flow integrity feature in newer CPUs. In older CPUs, that's just a no operation. So right now on our system, that feature is not really working. We didn't enable that. You need to enable that feature in the CPU. Then you need the program should have those under BR. We will talk about that in control flow security. So now you can just treat that as a no operation basically. So at the beginning of this, remember right now ESP points to here, right? So previously, remember, this is a buffer, this is a saved EBP, this is a return address. Now EBP points to here. The return address higher than that. Now the first instruction is push EBP. EBP has a value 4As. We push it again. So 4As goes to the stack again. So now we have two copies of 4As here. Make sense? The next instruction, of course, after the push, ESP first move stop, right? So after that, we have move ESP to EBP. So both ESP and EBP points to this place. Okay. So compared to the previous function, the base address actually moved 4 bytes higher 4 bytes. So the reason is the compiler never generated a code like this. The compiler never generated a call function. When it returns to the beginning of function, right? The code compiler generate, if it calls a function, then when that function returns, it returns to the next instruction of the call. It's never at the beginning of a function. So we are exploiting this to go to the beginning of another function. Then, so from the point of view of print secret, from this function's point of view, where is its saved EBP? Its saved EBP is this place, okay? It's not the previous function's saved EBP, okay? It's 4 bytes higher. And because of that, then this function will think its return address on stack will be EBP plus 4, right? It's only EBP plus 4. Okay, so will be this place. And its first argument parameter will be 4 bytes higher. Okay, make sense? Okay. But you only have one chance to overwrite the stack. It was in the previous function in gets, right? You do not get 2 opportunities to overwrite. That's why when you overwrite this, you actually need to overwrite the buffer, okay? Then this saved EBP value doesn't matter. We just saw we were using 4As. Then this address, we need the address of print secret. Then this address, what is this value? What is this actually?
Return address.
That's the return address, exactly. That's the return address print secret we use, right? But in this case, we are not really using that, so the value doesn't matter. Then on top of that, we have the parameter for print secret. Make sense? So your exploit actually looks like this. Okay. Then let's say, okay, let's do a demo on the server. This is return. Flow return true. So when we run this program, it tells us where the print secret is. Then, but right now we do not know where the buffer, right? We only know the C code level, the buffer is 6 bytes. We don't really know how big that is, so we do an obj count. We go to the Overflow function. It's very small. Like I said at the beginning, it has as BR32. That's a security feature which is not enabled right now. Then we say there is a call. This is a call to gets, okay, the dangerous function, and gets only takes one parameter. And this is 32-bit version. So the parameter was pushed onto the stack. So if we do a backward trace or in program analysis, this can be like a backward, what is that called? No, it's called backward slicing. Yeah, there's an algorithm called backward slicing. Basically, in program analysis, basically give you one statement. You can consider the instruction of the statement here, right? But obviously, this applies to different programming languages. In assembly, let's say, giving you one statement, you go backward, the algorithm will find out what are the other related statements that eventually influence this statement, right? So here, the call, obviously, we know this function takes one parameter, so we're looking for how that parameter is pushed onto the stack, and we say, okay, the last push is a push EAX. Then what is EAX? EAX is EBP minus E. E is 14, right? E is 14, okay. Which means buffer at the C code level, we asked for how many bytes? 6 bytes. But the compiler actually gave us 14 bytes there, right? So we have EBP points to save the EBP. On top of that, we have return address. Then we have here, this is buffer. And by reading the code, we find out the buffer is EBP minus E, right? So this is EBP, this is EBP minus E, which means this part is 14 bytes. Okay. So we already know that. Then what are we going to overwrite? What? So this one, do we need to do anything? Doesn't really matter, right? Just garbage here. So then we need actually 18 bytes of garbage. Then we need a return address, which is print secret's address. Then what is on top of this? Exactly. This is what we just discussed. This 4 bytes doesn't matter. Okay. Then the next 4 bytes, we need the value 1, 2, 3, 4, 5, 6. Okay. So let's try that. So this one takes input from std_in. So we were piping into this. We use Python 2, easier. So first, 18 bytes of garbage, then the return address. So the program actually tells us the return address. Where is that? 38, 63, 55, 56. 38, what, remember? 63. 63, 55, 56. Is that correct? Yeah. Now after that, another 4 bytes of garbage. I just do AAA. Then we put 1, 2, 3, 4, 5, 6, 7, 8. So when we do that, we actually return to print secret, and print secret obviously doesn't know It equals return to, if it is called to, so you will check the parameter. So if we change this value a little bit, obviously it doesn't work. Let's say we change this value, it doesn't work. If we do not have those 4 bytes, it doesn't work, right? However, this is not the only way to solve this challenge. You already learned the other way to solve the challenge, right? So do we have to return to print secret? Our goal is to get a flag. What other ways we can do to get a flag?
Go to print flag.
Okay, we directly return to the function of print flag. Okay, that's one approach. What other approaches? Is there another place we can return to? So we were trying to return to the beginning of this function, right? What if we just return to after the predicate? Right? We can also do that. Okay, make sense? And let's try that. Let's go back to our. So first of all, so here you see when we do obj dump, we do not really get the runtime address. We only get the offset. So previously we return to where? We return to print secret. So print secret, the offset is 1338, and the runtime address was 6338, which means the base here is 52. No. 50, right? Because this is an offset, right? You add a 50, I mean, this byte is 50, right? Okay, now you know that base, then we add that base to another location. Let's say this is return to, this is print secret. This is here. Here we have a function call to print flag. Make it larger. You see that? Here is a call to function flag. What if we just return to this address? Then we basically skip the comparison there, right? So this address, runtime address should be 63.4b, right? Then the exploit will look like this. So we don't need those parameters anymore. We don't need this. We also don't need that. What's this? Oh, this is the address. This one we do need. So that will be 4D or. No, not both. Wait, secret. Yeah, 4B. Okay, 4B. All right, so we directly return to that call instruction. So after the return of Overflow, the next instruction to be executed is just the call print flag. Right? So still works. Then there is another place is just a print flag. Where's print flag? Let's say, where's print flag? Here. Here's print flag. Print flag is at 1260. So if we return to the beginning of that, because print flag doesn't take any parameters. So I forgot about the address. What's that? 60. 6260. Here. Yeah. 52. 6 should be 6260. Yeah. 62. Yeah. So we also get that. So actually, if you return to here, it should also work, right? Because this instruction doesn't do anything. Even if you return to here, it may work because why are we pushing EBP? We're trying to save the previous functions string. But now we are doing attack. We only want to call this function. We don't need to save those. So even when we do that, it may work. Let's say, I think 71 definitely will work. We skip one more instruction, which is not. So say 61 works. I think the next may also work. Let's see what's next one. 62, 72, 74. Let's try those. 72. 72 actually works. 74, I'm not sure if it works because I don't know. So 74 doesn't work anymore. You can say 74, what we have there is. So here we have an instruction push EDI. So somehow this instruction is usable. Okay. If we skip this instruction, we don't get the thing. Okay, make sense? Yeah. Okay, so we learned how to return to a function that takes one parameter. Then things will be much easier. And now I guess you already understand how we return to a function with multiple parameters, right? Because parameters, they are pushed to stack. Then you just put them on stack one by one. That's it, right? So the next example, same as the previous one. Obviously, you can also bypass this. The main function is the same. The Overflow is the same. The only difference is print secret. Now print secret takes two arguments, I and j, and they have a value, specific value. So if you look at the stack, that's where they will be at on stack, right? Okay, so I will leave this to you guys later because it's basically the same idea. Let's say this is overflow return 3. Okay. So far, those two examples are talking about 32-bit machine. So what if this is a 64-bit machine? Can we use the same approach? Why is that? Yes, because the parameters for 64-bit machines, they are not pushed onto the stack. Here, as an attacker, you have the ability to overwrite the stack. The parameters are on stack, so you have the ability to overwrite them. But in a 64-bit machine, the first register is in EDI, RDI, the second register in RSI. So no matter how many bytes you overwrite the stack, you cannot overwrite the register. Register is part of the CPU, stack is part of the RAM, right? So we need a new technique to do this. And that technique is called return-oriented programming. We will learn that in the second half of the semester. So at this point, you don't know how to hack that. Okay, so then we learned that we can return to one program, one function. Can we return to multiple functions? Actually, we can, right? So look at this. Let's say this is a stack of Overflow. Overflow has a buffer. There may be some padding, okay? This whole thing we can call it a buffer. We have the saved EBP has a value. On top of that, we have return address. We have the argument 1, argument 2 for that function f1, okay? Then we have one chance to overwrite, right? We can overwrite this one. Let's overwrite so after the epilogue of Overflow, so before that, EBP points to here. We just analyzed this. We know after the epilogue, the ESP will point to this place, not here, right? So for the next function for F1, actually this place will be treated as its return address. Okay, so for this function 1, its argument no, this argument is not F1's argument. This argument is Wolf's argument. Okay. So F1's return address will be here. F1's argument 1 will be here, right? So F1's return address actually overlaps with Wolf's argument 1. But if F1 doesn't have an argument, then we can put many different return address there, right? We can put return address 1 after each other. Then actually we can chain those functions together. We return to functions 1 by 1. Make sense? But if the F1 have that, the overlap, then we cannot chain them. If we want to chain them even on 32-bit machine, we need to use return-oriented program. Okay, let's say the next example. We want to chain those functions together. There are 5 functions. Wolf is the same. We have a buffer 6 bytes. Our main function prints out the address of all 5 functions. The functions we have is the first one print out knowledge, the second one print out is, then print out the power, France, bacon. Okay. The last one we have an exit here, so we're not going to get so the exit here is a C library function, but eventually it calls the system call exit. So whenever this is called, this function F5 doesn't return. This function doesn't return. When this is called, the process will exit. So there will be no segmentation fault if you somehow sabotage the F5's frame. Okay. The reason I add this one is also try to print out the values, because if we don't do that, the kernel, the C library will buffer the messages you are trying to print out on terminal. So you do not immediately say that. Okay. So usually you do not say that because you are printing out a lot of data. Here we're only printing out several letters. Let's say library buffer will actually buffer that. Okay. So the goal is to chain them together. Well, we want to print out knowledge is power, France is bacon. Okay, so that's what we're going to print out, which means when Wolf returns, we're returning to F1. F1 return to F2, F2 return to F3, then F3 returns to F4, F4 returns to F2 again because we want to print out is twice. The F2 return to F5, okay? And we are just going to put all of them on stack, right? So let's go to, this is chain 32. So this one doesn't really give you a flag, but in the homework, there's a similar challenge which gives you a flag. This one we only print out the strings. The one in the homework will print out the flag. The first thing we do is still we analyze how many bytes the buffer is. We go to Wolf. You can say, actually it's the same as the previous one. Yeah, C code level, we ask for C bytes, 6 bytes. But the compiler give us 14 bytes here. Okay. Then if we run this program, it shows us the address of all the functions. Even if the program doesn't show that, because we have the binary, we can debug this, we can figure that out. Okay. Then we chain them together. This one takes input from where? I think it's the same, right? So gets, so it's the same. First, we need how many bytes of garbage?
18.
Exactly, 18 bytes of garbage. Also override the saved EBP there. Then We need 6 addresses. So the first one is 2D 625556. Second one is 4A 62. Hold on, direction's not correct. Yeah, 625556. Okay. We can try this first. When we do this, go ahead.
You take opposite to the Indian conversion. 565562.
Oh yeah, my bad. So you see, that's why we get a segmentation for it. 625556. So technically, we already called 2 functions here. We return to 2 functions, but it's not showing that. See, it's not showing knowledge is. Right? The reason is the system buffered that output, and before the system has a chance to print it out, the program already crashed. So we do not see that. That's why the last function I have an exit 0 there. There are other ways to do this. You can, in C library, there is a function called set vbuff or something. Set vbuff, I believe. Yeah, I think it's this function, set vbuff. If we set the buffering to 0, it will always print out. But in the program, I didn't do that. Yeah. Anyway, so that's why we need to finish this. We have 2 addresses. We can actually first call the last address. The last one has that x is 0 to see if this works. So A1 62 5556. Okay, this should work. See? So when we do this, we print out the knowledge is vacant. But the last one we have x is 0 there. Okay. So let's say we need 2 more. So this one we need the 1, 2, 3. Oh, this is touch screen. It's actually touch screen. Okay, so let's say the third address 67 2 55 56. Then we have function 4. Function 4 is 4 62 556. Then we have function 2 again, so we just copy this one. Okay, so now we get knowledge is power, Francis Bacon. So by the way, if you don't know why Francis Bacon, just Google this. It's a funny story, and there is actually an online shop selling products. Knowledge is power, Francis Bacon. There's a funny story behind this. Yeah.
I don't follow how the second is printing out in France is how the is printing out.
This one?
Yeah.
Because this function, F2, this function prints out is, and we return to it twice. Right? Here, we return to it, 4A62. Now we return to it again, 4A62. So that function is returned twice.
Was this in the instruction that we should return to it twice?
No, we are returning to the whole function. We execute the full function there, but the function only has several instructions, very small function. The function itself is small, right? The function calls printf, which is a library function, and it calls a OS to print out things. It's more complicated, yeah. The function itself is small, yeah.
In general, whatever value is stored in EBP.
Yeah.
It shall be larger than ESP, right?
Yes,
Stack is growing.
yes, yeah.
Isn't there any check that the CPU checks that EBP is accidentally not within ESP?
That's a very good idea. So right now, I haven't seen any protection mechanisms like that. There are many reasons. For example, this is more like hardware and software co-design. So imagine the Intel engineers that design the CPU, they need to consult the OS guys, the compiler guys, how we should design this. So they have some kind of contract, right? The contract is, this is a calling convention. And to make this faster, the Intel guys, I promise you this, I provide those kind of features. But technically, the software guys do not have to implement it this way, right? The EBP, the register, can be used as a ESP. The ESP register can be used as what we're using as the EBP, right? It's just a name, right? So it's difficult to implement those kind of things. But I think that's actually a very good idea. That's a very good observation. There are many heuristics, those kind of observations in security, and we are trying to utilize it. They are not necessarily always reliable, right? They may be reliable in some cases, but those kind of simple checks, the benefits of those is it's very efficient. Later, we are going to say some defenses. Some of them have been deployed in all of our computer, from your laptop to desktop, but they are not perfect solutions. So many issues. Then there are some perfect solutions, even proved to be secure, but we never use it because they are too expensive. Okay, so we will skip the 64-bit because it's basically the same thing. It's just that the address will be much longer. Yeah, so you will try this in your homework. Let's see. Okay. Good. Would I get rid of this? So far, what we have learned. So last week we were. How do I hide this? The whole thing. Okay, whatever. So if you remember, last week what we did is we modify a data on the stack, right? We can actually also modify data in other places, but so far only data on stack. So what we learned just now is to modify a code pointer, right? The return address is actually a code pointer. It's an address of code. An address is pointer in C, right? There is a code pointer on the stack. We override it. We override it to the address of a function. Right? And how is that address used? Eventually, it is used by a return instruction. And the return instruction will take a value on stack and use that as a code pointer, right? There are other ways. The code pointers could be a function pointer. In C, there could be a function pointer. In one of the homework, you are going to do that. Then we just return to a full function. Then technically, we hijacked the control flow. That's why this is called the control flow hijacking attack. And previously, it was data only attack. So next, what we're going to learn is we're not going to return to a function. Because right now, we have a very convenient function there, which is a print flag. or print secret. Obviously, if you are attacking a real world software, it will not have convenient function like that for you, right? So we are going to return to something we call share code in this case. We're going to write our own share code, and that share code can do whatever we want. In this case, we are trying to do two things. One is to create a shell so you can type things, do whatever you want. Or second, we just read that flag file and print it out. That's it. So in return-oriented programming, which we will learn in the second half of the semester, we're not going to return to share code because you will not be able to inject a share code. And we're not going to, we will return to full functions, and we will also return to something we call gadgets. Gadgets are basically sequence of instructions. They are not a full function. They're just several instructions in the address space. And those instructions, the beauty of that is those instructions were not necessarily generated by the compiler. The compiler didn't really emit those instructions. Compiler emit other instructions. But if we jump into the middle of the instruction, there is an instruction 5 bytes. Compiler generated that. If we jump to the middle of that instruction, we're only using the higher 3 bytes. Then it becomes a different instruction, right? So that's what we're going to do in the second half of this class. Okay, so I guess it's still early, so we don't need a break. So next, we will learn how to return to share code. Now we already learned how to override at least one code pointer, which is that return address on stack. So this is our example, overflow return 4. We're actually using this example for many different attacks, and we're going to harden this example to add different security features on top of this app, and you will learn different attack methods. A very simple example. First of all, there is no print flag function anymore in the address space. There's no print secret in the address space. Only two functions, the main function and Overflow. Main function calls Overflow, that's it. No one asked me right now why I do not just put the vulnerability in the main function. Why do I always create a Overflow there? Actually, if I put the vulnerability in the main function, it will be a little bit more difficult, but it still works. That's because main function is the very first function. The C library calls your function, right? Then the libc will actually do some alignment on the stack, which makes things a little bit harder, but still it's hackable. Actually, I think next week there will be a homework. There will be the same program, 2 versions. One is a hard version, one is an easy version. The hard version, the program will do some alignment, and you need to bypass that alignment. So here we have Overflow. The buffer here is kind of big. We have 40 bytes. Then we have just gets. That's it. Very similar to the previous one. Buffer is a little bit bigger. Print flag, print secret is not in the address space. Okay. So we already learned how to overwrite the return address. We already know how to do that. But what do we want to overwrite in this case? What is the value we want to overwrite? We don't have print flag anymore.
Can we overwrite the return address with print flag if we can find it?
We don't have that anymore. Yeah. There's no print flag.
The print flag and the address of the flag.
The flag is not in the address space.
Oh yeah,
The flag is in the file system.
it's in the file description, like file path, right?
Yes.
Can we use that like F8 for example?
Yes, what?
Like using like other functions,
Yes.
like F8
Yes.
for example.
Yes. So basically, because there is no print flag function in the address space, we're going to write our own flag, print flag function, and inject that into the address space. And there could be other C library functions already there we can utilize. That works too. So this is what the stack looks like. We have the buffer, we have saved EBP, we have return address. What we're going to do is we can override anything starting from this address, right? That's what we can do. We're going to develop something we call share-code, which is a piece of code, basically a sequence of instructions. And those instructions will give us the flag, okay? Those instructions will give us the flag. And we can put that instruction in many different places. First, we can put those instructions in the buffer, right? Because this is a place we can override. We can also put the instruction higher than the buffer, because that's also a place we can override. Make sense? Okay. The difficulty here is we don't really know where the share code is, right? So for example, this example, let's say this is buffer. The buffer's address, we only know a relative address. We only know it's EBP minus E. We don't know its absolute address, right? But if this return address here, it has to be an absolute address. Yeah. If we jump to here, we don't know the address. How do we jump that? We can guess. We can write brute force to guess all the places, right? That should work. But what are other approaches to make the chance to hit our share code higher? So the approach we're going to use is called a lob sled. Lob is a low operation instruction. So in this architecture, there actually is an instruction called, which name is lob, and its machine code is 90. It's only 1 byte. It doesn't do anything. It just goes to the next instruction. Okay. But there are many other instructions. You can treat them as null as long as they do not influence your code, right? So what we can do is we can put a huge lob in the front of our share code. Then we only need a rough idea where our share code is. So as long as we return to the middle of the lob sled, it will keep sliding eventually to our share code. So we don't need to know the exact address of our share code. Yeah, go ahead.
Sorry, can you say again why we can't just like write it at the end of the buffer? Because that's what we've been doing this whole time is we're saying like the buffer starts at EBP minus E.
But that's a relative address because you don't know the value in EBP, right?
But I know that it's gonna read it. I know it's gonna read in from the.
Yes,
And
but
the
when you
buffer.
override here, when you override that return address, you are overwriting it with a concrete value.
Yeah.
You cannot override it with EBP minus E,
Oh,
right?
I see what you're
Yeah,
saying.
it is a
okay.
concrete value.
Yeah, okay.
Yes. Any other questions?
Why can't you, why can't you just use the load effective address or? Like,
Let's say, how do you use that load effective address? That's an instruction. How do you execute that instruction? Right? So even for the same program, the same binary, you are running on different machines, or even it's the same machine at different time, those EBP values will be different. Yeah. Because actually before you call this main function, the libc library will do a lot of things, including pushing the environment variables on stack. If you set an environment variable in your terminal, those addresses will change. And here we're not even talking about the security features to intentionally randomize the addresses yet.
Maybe even if we have like this slide, if it's like a very large
Yes.
space, how would you still guess
You-
where to?
So you still guess, but the chance will be much higher. If your sled is huge, let's say your share code is like 20 bytes, but your sled is 2,000 bytes, right? And you know roughly where it is, then the chance will be much higher.
How do you know roughly where it is?
We already know where the stack is at the top of the memory address space, somewhere FF, right? Starting from there. Yeah, and also you can debug to print out But that address, when you debug it, you can see where the stack is, but that address will be different from when you do not debug this, but you get a rough idea where it is, yeah. Okay, so next we talk about our first share-code. We actually discussed about this a little bit in the first class. And today we are going to understand every byte of this. Okay. So this is the share-code we are going to use. Well, this is actually the baseline share-code. It's not the one we're going to use because it doesn't work anymore. But this is the baseline share-code. This is only 28 bytes. Okay. And how many instructions are here? Maybe 15 or 14 instructions. Okay. There are 14 instructions here. We go through them one by one. First, the idea of share code is to, in this case, we're trying to get a shell. What is a shell? Shell is a program, right? In this case, we're going to use bin sh as a shell. There are other shells we can use, but to make things simpler, we'll just use this one. Then how do we create a shell? We basically execute the program. So in C library, you have many functions to do that, but eventually boils down to the kernel or the interface of kernel. It's just one system call. It's the execve with the name of the program, with the path of the program. That's it. Okay. So if we write assembly code, that's what we're going to write. So, and that piece of code, 15 lines of instructions, will create that execve. Actually more than that, but we'll talk about that later. So actually, those three instructions don't do that. Those three instructions are not necessary. So the share code can be even smaller. I think in this code, the share code can be 23 bytes. Yeah. So if we remove those three instructions, it will be 23 bytes, something like that. Okay. So before midterm, we actually have another session just to talk about share code. And you are going to develop your own share code. We're going to develop all kinds of share code, including very small ones, like 12 bytes, 16 bytes. You are going to, use your creativity to make it much smaller. Okay. So then let's look at this. What we are trying to do is to make a system call. We'll make in the execve system call. And we are giving the system call one parameter, which is the address of that string. Okay, we're not giving the string directly. When we say it that way in C, it's actually the address of that string. So that system call is execve, and its system call number in 32-bit machine is 11. Okay, which means when we make that system call, we need to set register EAX as number 11. We need to set EBX as actually just the pass. Then we do not need to set other registers. It doesn't use that. Okay. If you look at the C prototype of this equivalent to the system call, it can be a little bit more complicated than this. It can take more parameters. The first one is pass. The second one is argument, the argv actually, right? But in this case, we're trying to get a shell. We don't set the command line argument. You can also set the environment variable. In this case, we don't need those, so we set all of them as 0, okay, because they're pointers, right? Then this one, because this is not a function anymore, this is a system call. It has a different convention. We're not pushing those parameters onto the stack, okay? We're directly setting registers to do that. So the first one is the address of the string or path of this file, which is /bin/sh. It's a string. We need the address. We put that address in register EBX. The second one is,
Is there no exec v syscall here? I'm not seeing it in the list, but I'm curious why we're using the VE version if we're not going to use the environment.
So actually at the system call level, it's only one thing. It's EXE, what's the name is called? It's actually called EXE7E. But if you program in C, you probably know, especially you program shell before, you know there is a family of functions, right? It's called EVE, EXE, ELE, there is a ELE, yeah, there is EVE. They just take different format of the input, the list, arrays, different things. But eventually, the system call is the same system call. Yeah. So doesn't really matter. Yeah. So then we can have the argv. What we can do with argv is, if we follow the convention, what is argv 0? The name of the program, right? Argv 1 is the first command line argument, right? If you follow that convention, then you can set those addresses, or just put it there, doesn't really matter. Okay. Then environment variable, if we don't want to set it, we just put 0 there. Because they're all pointers. Okay, so let's take a look at this in, let's see. Assume the CPU is executing from this instruction. We somehow already inject this to the address space. We will talk about this later, how we inject this. The first instruction is exclusive over EAX. So after this instruction, the EAX register will have value 0. That's it. Oops. Yeah, I skipped something. Okay. Now after that, we have push EAX. So this is what the stack look like. ESP points to some place. We don't really know where it points to, but it points to some place. We push EAX, then we put 4 bytes of 0 there, right? Then after that, we are pushing those 8 bytes there. Okay, we talked about this in the first class. That 8 bytes actually is a /bin/sh. Maybe there are 2 slashes. So actually there are 2 slashes. But I showed you that no matter how many slashes you have, they are the same. Then after that, you can say we have a string which is bin/sh. Then it's a 0 ending string. So that follows the same convention because we put 0 there. After that, after the push, ESP points to this place, right? Because that's a push. So ESP points to this, and ESP points to the string. ESP has the address of the string. And that's what we need for the register EBX, right? EBX is the address of that. So that's why the next instruction we do is, we can skip this. The next instruction we do is we move the value in ESP to EBP. EBX. So now EBX points to the string, okay? Then we move EAX to ECX, and EAX has 0, so ECX has 0, and also EDX 0, okay? So after this, we finished setting up those registers. We finished to set up EBX, ECX, EDX. But we still need the instruction, the system call number, which is 11, right? That's why we move B to AL. B is 11. Now we have all the registers set up. We just make a system call. The system call is, the instruction is int80 in Linux. Other platforms or even Windows, previous 32-bit Windows use a different system call number. Basically, it's an interrupt. Okay. So after this instruction, what happens? If it's successful, what happens?
Move to the shell.
What?
Move to the shell.
Okay. So if this is successful, the current program will be replaced as a shell, right? Okay. Then we have 3 more instructions here after this. Why do we have those 3 more instructions?
Return back to the program.
What?
Return back to the program.
But this is a piece of code, right? This is code is in the address space. If that int80 is successful, this program is replaced. It's not there anymore, right? So how can you return to that?
Yeah,
It's not there
When
anymore.
it's failed.
Yes, exactly. What if this one fails? It will return to here. Okay, it will execute the next instruction. Then what we are doing in the next three instructions is just to clean up things. So it will not show a segmentation photo or whatever. It will just exit gracefully. So this part is not really important in our class. Yeah, but if you are trying to hack someone and you want to hide your trace, that's what you want, right? So then let's say the next three instructions, so after we return from this, the return value is also in EAX. It has some error message, error code, okay? And we don't want that, so we exclusive OR EAX again, we get 0 there. Then we increase EAX. So EAX has a value 1, right? So what is EAX? It's a system call number, right? Go back to our table. EAX1, that's an exit system call. So I just then we do int 80 again. So that's basically that's a shellcode. That's 23 bytes, 12 instructions of shellcode. Okay, another question for you guys. Why we are doing exclusive EAX? Why don't we just move 0 to EAX? It's the same thing, right? We're trying to set EAX as 0. Why don't we just move EAX to 0 to EAX?
Faster for the hardware,
What?
faster for the hardware to do it.
No,
If we put 0, then it will go as a value. Here we're just setting it as.
no, that's not the reason. Yeah. What was the first vulnerability we saw in this class? What was the dangerous function? Exactly. When will string copy stop? Stop when there is a 0, right? So if you have a 0 in your shellcode, what you are attacking is a string copy. It will not copy everything. It will copy, in this case, the first one is there, so basically it will not copy anything. So that's why we're trying to avoid the 0 here. Okay. But in the shellcode class, we will have many other constraints. So you are going to try to avoid all kinds of bytes there as well. You are going, even there is a harder one, you need to make your shellcode self-modifying. Yeah, because you can say this one, the int 80, this instruction's machine code is CD. Okay, so it's the higher 127 possibility in ASCII, right? CD is a big number. So in one of the shellcode challenges, I will only allow you to use printable ASCII characters, like 1, 2, 3, 4, A, B, C, D, those ones. So CD is not printable, so you cannot use that. You cannot use CD directly in your shellcode. Okay. However, you have to make a system call. You have to use that instruction, right? So the idea is the first half of the shellcode is going to change the second half of shellcode. So when the shellcode is loaded in the memory, we will check if it has value like CD. If it doesn't have that, it passes. But when you execute the first half of the shellcode, it will change the second half. Then you have a CD there. Then you can make the system call. Okay, so that's the idea. Okay, now you understand your first shellcode. Any questions? Okay, well, good. Yeah.
Could you go over the string copy 0 part?
So string copy string copy takes only 2 parameters. One is the source destination, another one is source address and destination address. It will copy whatever at the source address as long as it's not 0 to the destination. If it's 0, it stops. Yeah, that's why if our goal here is to, let's say, imagine the first example, string copy is a function called by vol_foo. There is a buffer. We want to use that string copy to copy our shellcode onto the stack, right? If there is a 0, then it stops in the middle. Yeah.
I've seen that in the assembly code, and I assume It's not programmed specifically to allow that kind of vulnerability. So I see why we would want to use that for our own purposes. Like,
What do you mean?
I've seen the XOR EAX
Yeah.
in assembly code that's
Yes.
been disassembled.
Yes.
Why would someone put that?
That may be related to what you said there, maybe faster, I don't know. Maybe it's faster than move 0 to EX. Oh, I think another reason is really will be much smaller actually. So exclusive OR EX is probably 2 bytes.
Oh, because
I think-
doesn't need to have a 0.
Yes, I think those two, probably 2 bytes. I think that 50 is actually the push EX 1 byte. But if you move a 0 there, the value itself is 4 bytes, right? Then the move takes another byte, at least maybe 5 bytes. So actually it will be smaller, I think, yeah.
Can we talk about the, where you have the string for the shell code, what all of that is translating to, like what's X31 there? The like hex code in the shell code,
Oh, so like this one,
yeah.
okay. That is,
Go for it.
It's like
most
two
of those
outside.
are just machine code, right? So that's exclusive or EX, that is just 31C0. That's just 2 bytes. That's just the Intel's encoding, okay? But this one here, this part, push is an instruction, the operand is a value, so that's why you can say those values here,
Yeah,
here. 68 to F. Maybe from here, yeah.
okay.
There are many online assemblers. You can put the instructions there. It will show you the machine code, and also you put the machine code there. It show you the assembler. Of course, you can also use just obj dump. So what obj dump is doing is basically reading something like this and gave us the instructions, right? So I think let's see. Let's just use any of those. So obj dump actually gave us the machine code. This is the machine code part. Just that so far we're not really looking at this part. Okay, let's take a break, I guess. We come back at 7:20.
Yes, I wasn't here.
Did they last off?
Yeah, I didn't call. They called. So next question is pardon. Oh, someone in the data doing you can actually hear. Yeah, but we started not ChatGPT, not Flow, Gemini. That's for businesses. Targeting customer support, education. I started the next day. Yeah, I applied here, I was thinking, that's why I applied here. Thank you. That's why I went back. Actually, I still applied for summer, but I'm still closed. No.
Yeah. I feel like they're committed out there. Oh, yeah. Oh, man, what a world. That quite hits like pre-COVID. Yeah, okay. I mean, I'm all, my parents. It's like, I mean, like, it just helps. You know? It was like, I drew the homework, I was done with the homework. Day of morning maybe, I did not get anything. I was like, I did that. You got the list, you know? Every single day I come to work, I remember something else that I have to do. And it goes like this, and then I just look at it at the end of the day, and I'm like, it's also like now I can do it. It's like answer text. Yeah, yeah. How you doing? Oh, no. I know.
Yeah.
You just need a little bit more time.
I know, yeah. So in that. Sufficient time to find stuff. And then we took the ride.
So I did like literally sitting off the sitting like taking me to like.
I like those.
It's not one idea. Yeah, so far it's the program name for us is that's the opportunity for yeah, so they're happy to your football and they're
Starting where? I used to watch,
like every episode is the exact same. It's like
Nothing ever happens.
they made like a new.
There's a
Rocket comes, like 10 minutes.
I think they're on, there's only like.
Yeah, walk.
I have no idea that there was.
Just like in the background.
I haven't watched the Office in a long time, but it's.
Okay, so, going back to this example, let's say how we can inject our share code. Actually, we are using different versions of share code, a little bit more complicated than the one we used, but you get an idea, how do we write a share code? We boils down to what kind of system call you need, and write at assembly level. We don't use say library functions because this it will make our share code much smaller. Okay. So here the waffle has 40 bytes, and where it gets there. So the stack looks like this. If we look at the binary code, we find out there is a call to gets, then push EAX. EAX actually has a value of EBP minus 30 in hex. 30 in hex is 48. Okay, so the buffer in this case, we ask for 30 bytes in decimal 30. The compiler actually gave us 48 bytes. 48 bytes, that's actually good enough for our share code. Our share code is like 23 bytes. So we can actually put our share code at this place. But the challenge is we don't know the address, like we just talked about. We don't know the runtime address of that place. We can put the share code is 23 bytes. In total, there are 48 bytes. So we actually can put share code at this place. Then we have 25 bytes of knobs, but it's still a very small knob. We still need to get very accurately there. Instead, what we can do is we put the share code at a much higher address. We just do not use this space, put garbage there. Those two, the save the EBP, we don't care. The return address, we care, okay? Next class, we will talk about how we do not have the ability to override the return address. We only have the ability to write the save the EBP. We can still hack this, okay? Then we can have a huge knob set here, like 1,000, 2,000, even bigger, right? Then we put the share code there. Then it will be much easier for us to guess. Okay, so the share code we just looked at is this one, which is without those last three instructions, 23 bytes. This share code actually doesn't work anymore on our server. The reason is we're only making one system call here, which is EXE here. And in our current Ubuntu system, we're using a Ubuntu system. If you make a EXE system call, the OS will drop its privilege. So before you make the system call, EXE, that particular system call, okay? Before you make the system call, you are a set UID program. But after you make the system call, you're not a set UID program anymore, okay? So that's a problem in the current OS we're using. This is also a security feature. So previous versions of OS, 4 or 5 years before when I teach this class, this is not a problem. Okay. So, but we can easily bypass this. The way we bypass is before we make the EXE system call, we make another system call, which is set REUID. Set the real and effective UID, okay? The first one is real UID, we set it to 0, I guess. Then get effective UID, which is the current one. So we make that system call. So actually, there's also two system calls. The one is get EUID, the next one is set REUID, okay? After we make those system calls, we execute this EXE7E, then we can get a shell which has root privilege, okay? So this is basically, you can, in this class, you can copy those shell code. That's a shell code, it's here. You can just copy that, okay? And this is a disassembly of that, so you can say there are two more system calls. Another way to do this is we do not make the EXE7E system call. To make things much easier, we only read the flag, the printing out. We do not create a new process there, okay? How do you read a file and print out the file content in C programming?
File descriptor.
Yes, you first open, right? You first open, then you read. Then what's the third one?
Read it.
Right,
Yeah.
or puts, whatever. So eventually those are three system calls: open, write, open, read, and write. Of course, when you're programming C, you do not directly use system calls. You use functions. The write could be just a printf or fputs, something like that. The disadvantage of that is when you read, you need to read that into a memory region, read to a buffer. The content of that file read into a buffer, right? Then when you write, you give that buffer's address to write. Okay. There is actually an easier way to do that. There is a less well-known system call called a send file. The send file system call basically is read and write in one system call, and you don't need a buffer in the user space to do that. So in this case, we first open that /flag. We open and say what kind of permissions we have there. Then we just use the send file system call. The send file system call, the first argument is the destination. In this case, we are sending out to std out, which have a file descriptor of 0. That's why we have 0 here. Then open, this function will return the file descriptor of the open file, right? So we are basically opening a file and sending the content of that file, is a return address here, return value here, to the file descriptor 1. Okay. So we don't even need to know what is the file descriptor of open in this case. At the C code you don't know, and when you code this, you need to code that part. Okay. Then exit doesn't really matter. Okay. So that is those shellcode. Then we're going to use those shellcode on our return for challenge. Let's first use this one and show you that you can get a shell, but it's not a privileged shell. Okay, you can actually get a shell. Let's say this is a shell code. Okay, looks good. Return 4 or 32-bit. So when we run this program doesn't give us anything. What are we trying to do? We're trying to figure out where our shellcode will be, right? Okay. Then let's use GDB for this one. We debug this program. We set a breakpoint. Use B to set a breakpoint. Set a breakpoint at the beginning of Overflow. Now we set a breakpoint. Then we run this program. Use R. Now the program is running. Now in this program, we have that buffer, right? We have the buffer. Then we can just get a rough idea right now where the stack is. Okay, we can just do a P ESP, print ESP. Okay, so that gives us at this moment what register ESP points to. So when we do not debug this program, when we run that program, it will have a different address, but we know that it's probably just several hundred bytes off, okay? It will not be like several megabytes off. So we have a rough idea of this address. Then we're going to have our exploit. This one is fgets. So this is what our exploits look like. Oh, we forgot to check the buffer size. Did we just do something with that? Oh, we didn't. It was on my slides. Okay, so this is Overflow. The buffer is at EBP minus 30, okay, which is 48. Then we have the saved EBP, which is 4 bytes. So we need 52 bytes of garbage, right? Then we have the return address. Okay, let's see. So we have Python 2 first. We print out 52 bytes of garbage. Then we have the 4 bytes address of where our shellcode is, right? Our shellcode, the rough address is FF. So we have something like D6 maybe? D656. So it doesn't have to be accurate anyway. So we try D6 first. Here we just put a random value, doesn't matter. Then, like I said, 90 is the instruction knob, okay? Let's have a huge knob. Let's try 2000 bytes, okay? Maybe 2000 would be enough. Then we have our shellcode, okay? After our shellcode, we actually have another cat here. That's another system saying if we do not have the cat, the file descriptor will be closed. You do not have a chance to input to your shell if it's successful. Then we just have this pipe this into the program. Let's see if it's successful. No, illegal instruction. Okay, so when we do this, we got an illegal instruction. What does that mean?
We went to the wrong place.
Yes, we went to a wrong place, and at that place, those bytes cannot be interpreted as legal instructions, basically, right? So just change to a different address. Should we move higher or lower? So the address we get before was in GDB, and GDB usually will be lower because GDB will push more data on the stack. So we should maybe go to a higher address. Let's say, let's make the knob state even bigger. So D6, let's use D9, make it higher. Oops. This 5000 is too big, I think. The shell doesn't support that 5000. 4000 should work. Okay. Segmentation fault. Not lucky today. Let's try a lower address. So previously it was D6, right? Now we switch to D3. Any problem here? Something looks good, I think. Any syntax error? FF D3. Try to deny. Maybe E1. Much higher address. What other errors we have here? 52 bytes, return address. After that, we have log. Then we have our share code. our share code looks correct to me. So previous was D6, right? I'll just say 5. So you see a lot of guessing involved here. Say D, E. Well, that's too big. Changing too big. How many bytes are there? D1. Say E would be smart. Okay, I guess we need to debug this to say whether our share code is working first. Okay.
Professor, I have a doubt.
Yeah.
If we are using the output director so that the Python statement goes into the buffer overflow, we don't have to input anything afterwards for it to run, right?
We do not input anything else.
Yeah.
After we will get a shell, then we will be able to type.
So it's like something wrong in the command because you have to type something again so that you get segmentation fault. Like,
Oh no, that's because we have a can here.
oh,
Yeah, we have a can. Yeah.
Shall the shell code be higher or lower compared to this no operation code buffer?
I think it should be a little bit higher because the address we got was in GDB.
The order of the shell is before shell code, shall be before the no operations window that we're.
Should be after.
After,
Yeah.
so higher address or lower?
Should have a higher address than the lobster. Because you start executing on a lower address and keep going forward. Right. So let me double check this. Because our system also have other security features. Every time we reboot it, so every semester it will have a different address. So we need to figure out the address. Let me check the code again. So the code we have is fgets gets. Okay. Okay, we can debug. So let's say how we debug this. So we were involved. Like this. Okay. We can debug it this way. Let me copy this part. Why do we have a cat there? So that is because the new program, the shell, will need your input. If we do not have the cat, that the file descriptor will be closed. So you'll never have a chance to input. In the homework, actually, I give you guys a reading talking about why we need that. Yeah. It's not really critical here. Yeah. We GDB this, we run this program. When we run this program, we want to input this. Oh, let's set our breakpoint first. Lawful. Okay. Then we run this program. Okay, we are going to execute this Python script first, which gives us this address. Let's use that D6 something. The address we had was D6. Yeah, D6, but then it should be higher because well, our lob state is much higher than that. Let's use DT. That's not too big. Right. Okay. Now we are in lawful. We set a breakpoint at the end of the lawful. We set a breakpoint here. Okay, we use C to continue. Okay, now, oh, this is we got a segmentation fault. Oh, we got a segmentation fault before we return. That's weird. Did someone change this? Are we using a, okay, let me check if we're using a correct one. Return 4. overflow return for, because there are many different versions of this. We were using this one, right? Overflow return for. Okay, yeah, we are. But before that, we get a segmentation for it. Maybe it's because, let's say, maybe it's because our input is too long. We have 4,000 bytes of offset. Maybe that's too long. Let's try this again with a smaller one. So 4,000 maybe too big. Maybe the problem is use 1,500. Okay, we are in Overflow. Set a breakpoint at this place. Was there? We continue. Oh, looks like we haven't executed return yet, but now we do not get that segmentation for it, so it may work. Okay, so what instruction should we use here? I mean, command we should use instruction here. Yeah. We use step, which is the next step. We use step I. SI means step to the next instruction. Okay. So now we are at this address, CE44. Okay, it's probably the wrong address. Yeah, then we want to check if at this address we have our shellcode. So because this is not a function, we cannot do this symbol. We use the X instruction. X, we examine 10 instructions at the current address. Okay, so you can see that's not our instruction. Okay, so not our shellcode. Our shellcode should be 90, no, right? So if we continue execute here, we get a segmentation for it. But we can start again. We need to change the address. Forgot to change the address. So let's use DD. Okay, this may work. Start from beginning. Now we're at this is the return. We do a SI. Let's examine this instruction at this place again. DD, we still do not get that. So what was the address? Here we have 60. That's wrong again. Say at the beginning of Overflow. So now we're at the beginning of Overflow. We print out ESP D6, and we change to DD. How big is DD to D6? Oh, that's much bigger than 1,500. Right? From D6 to DD, so that address is probably too big, too high. So 6 there, that's maybe 8. 8 makes more sense. So we continue. So this one we do SI. Now we examine instructions. Yeah, that's our shellcode. Okay. So if we execute here, so technically, say it will execute a new program which is being SH. However, this is GDB, so it's not setUID. So even if we get that, it will not give us a privilege. That's why we need to do the same thing outside. Okay, so we find out that this one cannot be too big. Too big, it will trigger segmentation fault. So this one, let's try maybe from D8. Okay. Oh, actually it works. Okay. However, like I said, this is a simple 23 bytes shellcode. So if we do who am I to figure out who am I? We're the user CTF, okay? We still do not have the privilege to add the flag permission deny, okay? That's why we needed the next share code, a different one. So whenever you encounter some problem like this, use a debugger, okay? Debug, you figure out what's going on. Let's say, let's first use the share code. Oh, this one works. Okay, this one. 3 system calls. Let's use this one. White space, need to remove that. Other white space, need to remove. Everything looks good from here. So this one, the address, we're going to use D8. That's what we got. Random one. D8. That's right, D8. FF. 1500 here. Everything else looks good, I guess. Okay. Yes. Oh, works. Where am I? Where are the roots this time? Right? So only cat flag. So that's how we get the flag. Okay. So because we make the system call exe you want to drop our privilege. That's why we need to do this. Okay. If your goal is only to get the flag, you're not trying to do anything else. You don't really need a shell, even though it is called a shell code, because traditionally, historically, you want to get a powerful shell, do whatever you want. Imagine here, you get a shell. You can collect to a remote version, download the other things, anything you want. You get full control of the system, right? Now, if we go to the next long shell code, I call it long shell code because it doesn't give you a shell. It will only give you the flag. So this one does this. At this moment, you are not writing this part, but 2 weeks later, you are going to write this piece of code and make it smaller, do all kinds of other things. Okay, oops. Yeah, go ahead.
Could you summarize what went wrong and how you figured it out?
Okay, yeah, let's do this demo first. Then I talk about that. Let's say somewhere near. So you can see this share code is much bigger. Program name here is not correct. Fix that. Okay, so this one doesn't give you a share, and your permission was never downgraded. You get a flag directly. It should be the same flag if I'm not cheating. So let's say so here we have IZW, right? Here we have IZW. It's the same flag because the flag is retrieved from the file system. Okay. So go back to your question. So when something doesn't work, you just debug, right? You have the tools to understand every step what is going on in this case. So I first use GDB, but in GDB, you will not get a flag. Okay. I first use the same exploit, and I set several critical breakpoints because I have expectations at those breakpoints what I should get, right? I first set a breakpoint at the beginning of Overflow. From there, I can get roughly where our buffer is, right? Because buffer is at is in the stack frame of Overflow. Yeah. So when I execute Overflow that function, I print out where the ESP points to, so I get a rough idea where that is. Then after that, I set a breakpoint at the end of Overflow. My goal was to return from there, and it is supposed to return to our share code. But before that, somehow we get a segmentation fault. Right, before that, we have 4,000 bytes of knobs, and there we got a segmentation fault. So when we're not debugging that, we didn't know where is that segmentation. We only say a segmentation fault. But when we debug, oh, we realize, okay, actually before we return to our share code, we already get a segmentation fault. Okay, we probably overwrite something important there, right? Something quite important there, we overwrite. Then I decided to make our knob set much smaller in this case, so it will not overwrite something critical there. Then we, at the end of Overflow, we try to return to our share code. We tried multiple times to say what address we should use. Yeah, that's basically what happens. Any other questions?
My question is, whenever, is that the feature of OS when the exec PE is called, it downgrades your permissions?
Yes.
Okay, yeah, so whenever we call another syscall before we do that call, why is that not happening? Why aren't we getting?
So I think that's just a feature in that exe CVE system call. For other system calls, it's not doing the same, doing that. I think that system call is obviously different because it's replacing the current process with a new process.
Yeah, but what are we changing before that exact call? That is not letting that
We are
exact call.
basically confirming to the OS, this is our ID and real ID and effective ID. Yeah, yeah. Okay, so that's the 32-bit version. I showed you 3 different share code, and in this class, feel free to use them. Okay, then 64-bit. Actually, very similar idea. It's just first of all, the calling convention in the user land is different. Also, in the system call level is also different. But writing assembly code in 64-bit is easier than writing 32-bit. For example, this instruction here, not this one, this example. So here, this is the same piece of program, just a 64-bit version, and we can see that the size of buffer is the same. Okay, we have 48 bytes of buffer, but the saved RBP is different, that's 8 bytes, right? So now we need 56 bytes of garbage instead of 52. Previously it was 52. Okay. Everything else is similar. What different is the share code. This is our 64-bit version of share code. Several, you can say, first of all, it's shorter, and we have several instructions here, only 1, 2, 3, 4, 5. 5 instructions here. And we're not using int 80 anymore. We use another instruction. The instruction is just syscall, okay? But this is backward compatible. So actually you can still use int 80, okay? But I think if you use int 80, the system call number will be different. You can say here, the system call number is 59. It's not 11 anymore, okay? The interesting feature is this. To get the address of the string, you can use RIP plus that string's label here directly. So this is a syntax not available in 32. Okay, so that's why it makes things a little bit easier. So this is a assembly code. You can compile this code, use GCC to compile it. You use the option no std lib because you don't need the standard library. What you need is this piece of code. That's it, right? So no static library, no dynamic library. You compile this assembly code, you get an L file. Okay. After the L file, we talked about that. There are headers. There are a lot of metadata you don't need. What you need is only that several bytes of instructions. Then you can use the obj copy command to dump the .txt section. Because there is no library, there is no main function, this several instructions is everything, all the code in this piece of L file. Okay, that's how you get that. Of course, you don't have to use those tools. There are so many online tools out there. You just put the piece of assembly there, the instructions there. It will just generate the machine code for you. So that's very convenient now. There is a particular one I use a lot, but I think it is blocked in the Northeastern website. Let me try again. Online assembler. Yeah, this is the one I use a lot. Diffuse security, but I think it's blocked. Yeah, it looks weird, right? But it may work. Let's see. There are other tools you can find. Let's say Explore EAX. Let's assemble this. See? It's blocked by Northeastern.
You might be able to report it to Northeastern.
Because they were thinking this is an attacking tool. They do not, right? Those are hacking tools, basically. But there are other websites you can have. Let's say maybe this one works. Oh, this one should work. Yeah. So we are going to do, oh, this one is even more powerful. You can do all kinds of machines. Yeah, so you can just get the machine code. So you don't need to go through. So everything there is an online version, even debugger, everything, right? The disassembler, you're using binary ninja, everything, there is an online version. Yeah. So you don't really need to go through those commands. So, yeah. Let's see. The 64-bit, the system core numbers are reordered. I don't know why they did that. So now read has a system core number 0. Previously it was, what's that? I don't remember. Exit was 1. I don't remember what is 0. Now we are using EXE7E was 59. Okay. So this is a 64-bit version of the shellcode. I only did the long share code version. So let's try this. Oh, I actually did both. There's also a share version. Don't know the size of lobster yet. I want to fix this part. Here, 6. We go to the 64-bit version. Terminal. So we still need to find out the address, right? So we just do another GDB. This one. Set up breakpoint at Overflow. Let's run. Then we print out RIP, not EIP anymore, RIP. So we get that address. Oh, no, not RIP, RSP. Yeah, RSP, yeah. So that's the address we get there. Okay, so let's try. We can directly pipe it, but I want to put it in the file first. Yep. let's say 56, because 48 bytes of buffer, 8 bytes of saved RPP, 50x, then 8 bytes of address, right? Let's try that address. We have 18, that byte doesn't matter. So E5, let's go. Let's just use E5 first. FF, and F slots there. 6F. FF, 7F. Then how about the next one? So there should be 0, right? Because these are 8 bytes. 1, 2, 3, 4, 5, 6, 7. It's actually this, right? That's 8 byte. 1, 2, 3, 4, 5, 6, 7, 8, right? Then let's use this 150. And sometimes you can go higher. Okay. Then we pipe this into the program, see if it works. Oh, it works. We're lucky. Okay. So even for the, so I'm not going to try the next one. You can do this by yourself. This is basically another version of the 64-bit version of the share code. Okay. Okay, so what do we have learned so far? We learned how to return to the share code. We learned how to inject the share code. Okay, in those cases, we're basically injecting a share code onto the stack. Because the vulnerable dangerous function there is gets, we can inject arbitrary lengths of data there. Okay. However, some challenges we encountered. First, we don't know the exact address where we should return to. That's why we did a lot of guessing. That happens a lot in hacking. Sometimes you don't even have the battery, you need to do a lot of guessing. And also, that can be considered as a defense approach to make it harder to guess those addresses. So one of the security features we will learn in the future is called address space layout randomization. They will randomize things, makes it even harder to guess where everything is. Okay. Also, if a set UID program is replaced with a new image, the new process doesn't inherit the root privilege. That's why we need to make those two system calls to confirm to the kernel we want the privilege. Okay. Next, we are going to learn some other tricks. We learn where else we can put our share code. Yeah, go ahead.
What's the point of it not inheriting root privilege if you can just change that? Like, that doesn't seem like a good security feature.
Yeah, right. It's not it's bypassable. Yeah, like all other security features, it's bypassable. I do not really know exactly why they designed that way. Like I said, there were, even now, I think there are Linux distributions, versions that will not drop your privilege. But the one we are using right now does drop your privilege. Yeah. But like I said, even other security features seem like more advanced, they can be bypassed. Okay, so we will learn how to put share code in other locations. Okay, I always do this kind of practice myself. Is when we discover a new attack or an existing attack, we try to understand it more deeper. I always write something like this, like what kind of conditions, prerequisites we have, so we can pull off this attack. Then we write down all kinds of conditions one by one. Some of the conditions are actually implicit. You never really think about that. So why do I write them down? Because after you realize those are the conditions, you take out one condition, you come up with a new defense. It may not be a perfect defense, but it may slow down the attackers. And it may be a very, not necessarily super effective, but it can be a very efficient defense. And those efficient ones are really deployed in the system, not the perfect ones, okay? So far, let's say, what kind of abilities we need as an attacker to pull off the attack we just saw. First, we need the ability to put the shellcode onto the stack, right? So far, we're using stack. Then it also implies that the stack is executable. Right? We're putting code on the stack, so we're executing from there. So from OS point of view, stack is just a memory region, and that memory region from OS point of view is executable. Why it should be executable? Why should we ever have code on stack? We should not, right? That's why existing OS, right now, current OS, the stack is not executable. And that started from a hardware feature we have maybe 20 years ago. Yeah, we'll talk about that later, maybe next class. Also, we should have the ability to overwrite the return address on stack. At least one return address on stack. And that return address eventually will be used by a return instruction, right? And then eventually we need to give the control to the shellcode. So there are many ways later we will say we were taking out those conditions one by one. We can see different defense techniques. So sometimes doing security research is very simple. If you list something like this, you can write so many papers. Take out one, you get write a paper, right? But of course, what we're discussing in this class is like something happened in the last 20 years or even 20 years ago. So next, let's learn how to inject the shellcode in two different places. One is environment variable, another one is command line arguments. But both those locations are actually still on the stack, okay? Environment variables are actually on the stack. Command line arguments, the same, okay? We skip this part. So I mentioned about this many times. As a C developer, you develop the main function. To you, that is the first function. Your main function calls all other functions. That's your entry point. But for the program, it's not. Okay. For the program, for L program, the entry point is actually underscore start. Okay, that's kind of the standard. The OS will look for that entry point, and usually that place is named underscore start. At this place, that underscore start is not necessarily a function, maybe just some code. But eventually it will call the C library function, which is underscore libc start main. Okay, that's a C library function. And that C library function will call your main function. That's why when you program the main function, you have argv, argc there, right? That's your parameter. But when the libc start main calls that, it will give you those parameters, obviously. Okay? It will specify those parameters. So, because of that, you can imagine before your main function executes, the stack has already been used because there are so many functions being called, returned already. Okay. So the stack actually looks like this. Before your main function executes, the C library functions, they will copy the environment variables from the system to the address space of your program. It will have something like this. This is high address, this is low address, so we should look at something like this. Okay. So let's assume this is where your main function stack is, right? So the main function also have a return address, right? 4 bytes lower is also have a saved EBP, right? Now 4 bytes higher than return address, it actually have its own argument pushed by the start C function, right? So those arguments are, the first one is argc, right? After argc, we have argv1. There is an array, argv1, argv0, argv1, argv2, okay? And many other argvs, okay? But those are pointers because the main function, the prototype is actually what? So it's char start arc v array, right? So it's an array of pointers. Okay. So a pointer is basically an address. That's why those are addresses, they're pointers. They're pointing to what? Pointing to the command line arguments, which are also strings, right? So those strings are somewhere up there. There are strings up there, and those are pointers pointing to those strings. So after that, to show this array end, there will be a 0. Then we have the next array, which is also a char start environment variable array. Okay, so it's another array of pointers. Okay, that's why we have many addresses here pointed to other strings, and those strings are environment variables. And the environment variables follow this format. There's a name, there's an equal sign, and there's a value. The whole thing is a string, right? But both of them are on the stack. Okay. So if we run this stack layout, I think we have a stack layout program somewhere. Layout. Okay, so we run this program, you can say, we are not given it in command line argument. So the only command line argument here is just the program name, right? So you can say argc is at this address, D6, P0. Value is 1, because that's the only command line argument, the name of the program. Then argv1 is the name of the program, the string. That's why we have this. We don't have argv1, so it will be set as 0, and also indicate this is end of argv. Then this one actually, that's because my program is hard-coded. Here is actually the environment variable now. So how many environment variables are there? At least we are printing out 4 of them at this time, right? One is, those two are actually the same address, that's why it's overlapping. Okay. What if we, let's say, we put 2 more, 3 more there? You can say, so argc is 4, argv1 is a program name, v0. v1 is the first string, is this string. v2 is the second string. I'm not printing out the third one. Then we have environment variables as well, right? So look at this address. Those addresses all start with FF. It's a very high address that's on stack. Okay. We can actually also debug this. Let's debug this. Debug, let's say this. We're going to run this program with, let's say, 2 arguments like this. Okay. Now we're, set a breakpoint first. Set a breakpoint at the main. When we run this program with those arguments. Now we are at the beginning of the main. Okay. What I want to examine here is from the stack of main, we go to higher addresses. And I want to prove you that eventually at those higher addresses, we should say environment variables. We should say the command line arguments, right? So we can just examine string because those are strings. So we do S. When let's say we examine 500 strings, S is string in this case, at where ESP points to. Okay. So at the beginning, you can say those are maybe just garbage. They're not necessarily valid ASCII strings, but we keep going up, maybe much higher address. See, what's that? That's the environment variables. We probably already skipped. Oh, here, that's our command line arguments, see? Those are so after command line arguments, we have environment variables, right? When you program this, you didn't put it here. The libc put it here, right? So those are in your address space. So I guess you see where I'm going. Then we can inject the shellcode there. We can put our shellcode there. Then it will be automatically loaded to the address space by the OS and loader. Okay? What's the benefit of that? First of all, you can say when we do that injection, we were limited to 1500 bytes of lobs there. The rest trigger. But here, I think we can have a much bigger lob slit.
We can't put it in the strings, right? Is that a read-only section?
What string?
The strings in between the environment variables and the RB.
So you need to think about what you can control, right? Before you run a program, you can set the environment variables in the current environment, right? That's something you can control. You can also set the command line. That's also something you can control. But what do you mean by strings there?
So my understanding of the string space with
String space?
just that there's a read-only section where strings.
Oh, okay. Okay. So that read-only section first is a segment in the L file, right? So that's part of the L file. And in this case, in our thread model, you cannot change the binary. In our server, you can run this program, but you cannot change that. Yeah. That's the assumption. There could be different attack models. In some assumptions, you can change the program. Imagine, let's say, for the challenges you have done so far, we are injecting shellcode. You cannot change the program. What if you can change the program? Then maybe there is a function call, and you just change that function call to call print flag. That's it. Right. Yeah. Okay, let's say, so this is overflow written 5. The difference of this one is the buffer is super small, only 4 bytes. Okay. Fgets is the dangerous function here. It reads 18 bytes, and that 18 bytes is only enough to overwrite the return address. If you look at the binary, so let me explain what is the fgets first. So fgets will read from a file string, then put that in a buffer. So in this case, this is a buffer, and we specify how many bytes we read and where do we read from. We read from stdin. Okay, I'm just trying to show you different functions. They all can be dangerous. Okay, so in the binary, we can say that the buffer is actually 8 bytes in this case, because here you can say the buffer is at EBP minus 8, okay, 8 bytes. Then the saved EBP 4 bytes, return address 4 bytes, that's 16 bytes already. And fgets, in this case, we're going to write 18 bytes, okay? However, fgets were always, at least in the Linux version, will always write 0A and 0 at the end of the string, okay? So it always will append those two. That takes 2 bytes. So basically, you can't overwrite those 16 bytes, okay? Which means it's not enough for you to put the shellcode here, unless you have 8 bytes of shellcode, okay? Which is possible. You can write out 8 bytes of shellcode. I have done that, but right now, the smallest shellcode you know is 23 bytes. So, okay, we're not going to do that right now. So that's why we want to put the shellcode in other places, right? We want to put them in environment variable and also command line, those 2 places. Let's start with, let's see, which one is this? Let's start with environment variable. Okay, yeah, go ahead.
So the stack that you showed before, is loaded in by the shell.
No. Yeah, loaded by shell. Yeah, you're right. So, it's not that accurate, obviously. So when you type the name of the program, the shell will fork itself, then replace itself with the program you want to run. Okay, so technically the loader, the OS, is loading the program from the file system to the memory, not really the shell itself. Yeah,
And a new shell will be, a new stack will be set up every time you run a new
it's
shell.
a totally new program. So after the exe CVE, it's a new program. After fork, it's the same program, 2 copies. Yeah. Okay. So the first one, we're going to do this non-share shellcode. We put it in the environment variable. We use the command export to define environment variable, a persistent environment variable. Then the name of the environment variable doesn't matter. Here I use S code in shellcode. After that, equal sign. Then after that, we run this Python script to generate that shellcode. Okay, that's it. After that, we need to find out where this shellcode is, right? That's why I have a very simple program. This program doesn't do anything else. It will print out where environment variable is. But this program will print out the environment variable's address for this program. So other program, when they get those environment variables, the address may be a little bit different, not significantly different. But we already solved that problem. We have a huge knob set, right? So yeah. So that's the idea. Let's say we're still using. We are still using return 4 for this one. Return 4. This is 32-bit. Okay, so we export this. I have huh? Oh, we already said that, I think. We have a small offset here, 500 bytes, not very big. Let's say if it is over there. We do print environment variable. And let's see, it's here. Because many of those bytes are not printable, that's why you do not say everything. Okay? You only say the first several bytes there. Then if we use a program, we have the program here. We provide several programs here for you. So there is a Rob gadget thing you can use later. There are get environment variable 32-bit, get environment variable 64-bit. So if you do get 32-bit, then you do S code, let's name that. Then you get the address. The address is somewhere here. Now what do we do? How do we hack this one?
This one based on the return address.
Exactly, right? So it's actually easy from here. So Python 2. Print. How many bytes we need? 52, right? I think it's 52. After 52, we have the address. So it's Okay, there is another thing I want to ask you guys. What is this address? What does this address point to? Pointing to that environment variable, right? But what is the format of that environment variable?
It's the string S code equals.
Yes, it's a name, the equal, then our share code. So this address actually points to where?
The S and S code.
The S code. It's not valid instruction. So if you jump to that location, it will be invalid instruction or segmentation fault, whatever, right? So you actually need to add some value on top of this. Make sense? Yeah. So you want to reach the lob state. Okay, so we want to try. Oops. Maybe something like that. When we type this into this, and it works, right? So our share code is, so in this case, in this command, we didn't inject the share code, right? The share code is already loaded to the address space by the loader because it's in environment variable. The next one is command line. Actually the same. So how do you input the command line? You just, even though this program doesn't take command line input, you can still give it a command line. The program itself is not reading from the command line, right? But if you provide that, the loader will be pushing that to the, so first let's unset this. So we do not, I think it's called unset. Okay, we don't have that anymore. We don't have that share code in the address space. Now we're going to inject this in the command line. So first one, we still need this part. Let's see. This, we don't need this. We don't need a Python there. We still need this input, but we don't know the address yet. But it should be an address much higher because it will be command line, right? So this address right now, what is this? Oh, this is the environment variable, so maybe lower than this. Okay. Anyway, then we are going to have our this part. Just put command line here. Let's see. Or we just need to change the address. This is the name of the program. The $, make sure whatever here is executed first. Then the result will be fed through the program as a command line argument. This part looks okay for now. Maybe make the lobster a little bit bigger. Okay. Let's try again. So then we need to adjust the address. The address was the address of environment variable. So maybe lower. Let's try to go lower.
Did you set the new environment variable anywhere? Or is it the no?
No, we didn't set the environment variable. We unset it. Yeah, we unset the environment variable. So the share code right now is here in command line arguments, this part. Yeah. We're just trying to figure out where it is. Obviously we can write a script to keep trying. Which try multiple places. Because our mouse set is big enough in this case, I feel. So every time we change this, we're changing 250 bytes, right? Something around 250. So we can maybe move a little bit bigger. I'm trying to move to a lower address, but maybe, oh,
There.
oh, it works, cool. So, yeah, no, I'm trying to show you I'm not prepared, so I'm not cheating here, so. Yeah, cool. Let's see. Okay, so this part we can skip for now because we can do this later. When in the share code class where you write your own share code. So we can say, this is basically what we discussed, right? We're changing the return address and change to gadgets. Okay, we still have a lot of time. So what do you guys want to do? We can talk about the next topic, but I think it may be too much to digest for today. Or you guys can start working on the homework and I can walk around then to help you with the homework. Yeah, I think that's a better idea. Okay, good. Then for the homework today, let me explain what we will do next week. Next week, we are going to overwrite the saved EBP. Right? So saved EBP technically is a data pointer, right? It doesn't directly point to code. So what data it points to? It points to the previous function's function frame. And that has its own syntax, basically. There's a return address, there's a lot of saved EBP, right? And that return address is a code pointer. So that's something we're going to use. So the next challenge, you do not have the ability to overwrite the return address, but only the saved EBP. Then we're going to use that. After that, we will talk about all kinds of defenses that most of them have been deployed in your existing systems, but not necessarily in some low-end embedded systems. That's why my lab, we're doing a lot of research to design new approaches to similar features in low-end systems. That's what we're going to do next. Then after that, will also be some defense. Then we will talk about how to write all kinds of weird share code and look at some real-world share code examples. For the homework today, let's see. Homework today, first two tasks are just simple ones. The third one is also simple. The fourth one is return 1, return 2, return 3, chain, return 7. And so basically only the last two tasks, challenges, I didn't demo in the class. Okay. Return 7 and reverse engineering 2. Those are the new ones you need to figure out. Cool. You can start wherever you want. You can try to replicate what we just did in the class. Because there are a lot of guessing, so there's no guarantee you can get it to the first time. So you can start from there. I can help you guys. We can leave around 9 o'clock, I guess. Okay, so now we'll stop the recording from here.